the bone marrow and the thymus. Now remember, we're fixing to talk about where certain lymphocytes mature at, but just remember all of them originate in the bone marrow. That's where they develop. Okay? There's no like certain other place. So all of your white blood cells, for the most part, are going to develop in the bone marrow, but there is a little bit of a difference about where they mature at. Remember the letter T. The T should go with thymus, all right? T lymphocytes, they develop in the bone marrow, but they mature in the thymus. Right? B lymphs develop and mature in the bone marrow. We are going to have to differentiate what are called, they're all lymphocytes, okay, but there's what's called T lymphs and there's B lymphs. And they have basically different functions. It does say that many die, some perform immune functions, and some form memory cells. We'll talk about those memory cells. That's where you get into the CD4 and CD8 cells. Your B lymphocytes, the primary function is to produce and secrete antibodies into body fluids or humors, and that's where they get the name humoral immunity from. It says these activated cells undergo cell division in which some cells become memory cells, others become plasma cells, which manufacture antibodies. Do you guys remember the plasma cell we showed you in hematology? It looks like a lymphocyte, but remember I told you that nucleus is kind of eccentric and it usually have a white halo around the nucleus. That's what a plasma cell looks like. It says antibodies or immunoglobulins produced by the B cells can either be expressed on its cell surface or it can be secreted by other plasma cells. It can also send signals to what's called T cells, which are functioning as antigen-presenting cells. This part right here, activated B cells, division in which some cells become memory cell, others become plasma cells. You need to highlight that, make sure you don't lose sight of that. Okay, your T lymphocytes, these are the major cells involved in what's known as cellular immunity. They possess a specific receptor for the antigen. Cells that leave the thymus do not become activated until they encounter that specific antigen in the peripheral or secondary lymphoid tissues. These are going to consist of things like the spleen, the lymph nodes, Payer's patches, and the tonsils. This, I may not even be pronounced Payer's patches, that's found in the small intestine. Okay, that's an area of the small intestine. It says it cannot attack the targets at a distance, they have to have direct contact. It says the surface proteins responsible for these antigens are going to be CD4 and CD8, which are subsets of T lymphocytes. So I want you to think of that as T lymphocytes. You also have cells that make up T lymphocytes that are called CD4 and some that are called CD8. CD4 cells are what's called T helper cells. They help other cells to mature, proliferate, produce cytokines that influence many other cells of the immune system. They also signal B cells to produce an antibody. Now, I have written in my notes to help me better understand that. Okay, you don't have to write this, but I have written down, basically these cells say, I'm going to help. You need to clone and make more antibodies. Remember what I told you? It's like they see an antigen and they're like, you know what? That can hurt me, all right? That's foreign. So they say, look, I'm going to clone some antibodies that are specific for just that antigen. So that's what they mean by they proliferate. They make more cells that can do a number on that antigen if it needs to. Now the CD8 cells, these are called the T suppressor or the cytotoxic cells because of their ability to kill cells that are infected or marked as foreign. It says the macrophage will ingest the antigen, it presents it to the T cells or the CD8 cells if the receptor fits, the T cell is activated and kills the target cell. So what I want you to think on there is on a CD8, what I have written down is it's like, okay, I recognize you, I know who you are, you know, like you're an intruder, and now I'm gonna kill you. All right, that's the difference in the two, yeah.
That's not the same as a natural killer, is it?
They have the same function.
But no.
But I wouldn't say it's the same exact cell. The natural killer cells, I believe, are part of the innate immunity. They actually are part of the primary, that it doesn't matter what type of antigen. They come in just automatically. Yeah.
So the CD4 ones, you said clone and make more?
Yeah, they're calling out for help. They're basically saying, look, I see something that's not right. I want you to proliferate. I want you to make more of these type of antibodies that can see this particular antigen, all right, to where it can bind to it, and then that's where those killer cells.
These CD4 T helpers, they're sending the messages out specifically, and here's my question. Does the message go into the B cells?
Part of the message is going to the B cells, but not all of it.
All right?
And another little side note about these CD4 cells, just to kind of help you understand, CD4 cells, they have such an important role, and unfortunately the HIV virus, that's what it hones in on, okay? And it basically destroys or it damages all of your CD4 cells, so now you're susceptible to anything because you don't have those cells. You have cells that recognize things as foreign, but you don't have cells that say, okay, I see the foreign cell, now I want you to produce 1 million antibodies that can take that out. And because of that, people that have the HIV virus, if it goes ahead and develops into full-blown AIDS, that's the test that they'll be doing a CD4 count on these people, because a CD4 low blood cell count, where they actually have a test where they can determine just out of your lymphocytes how many of them are the CD4 cells, and if that count is ever really, really low, that's an indication that you've got something going on in your body that's damaging all the CD4 cells, and that's never good. Okay. They can also use it to where there's certain times where you do an organ transplant, for example, to where they want to give you a drug that actually does cause your CD4 cells to kind of lay dormant for a while. Because the last thing you want is to be given a kidney, all right, and then your CD4 cells say, whoa, I recognize something as foreign, I need you to proliferate and start attacking that membrane complex, or part of that human leukocyte antigen that we'll talk about. That also plays a role. So there are times where you want your CD4 cells to not be activated. Okay, the major histocompatibility complex, this was once known as the human leukocyte antigen. These are proteins on the surfaces of tissues and blood cells that provide identity to a specific individual. This is what tells the body this is self. Do not produce antibodies to this. Okay? It can be very important in organ transplants. Immunity can be classified as innate, adaptive, active, or passive. Okay, there's a test question on this, so you need to pay attention here. Natural passive immunity, we're talking about examples of all different types of immunity, and this should make sense to you. If a mother passes her antibodies on to the baby, in other words, the mother has IgG antibodies, all right? Those antibodies are small enough they can cross the placenta and they can give the baby immunity that way. That's considered naturally passive. Naturally passive. Now, if, for example, let's just say that you go to an area that is endemic for the hepatitis A virus. And let's say you're very, very sure that you have been exposed to the hepatitis A virus. And let's say you've never had the vaccination or anything like that. They can actually give you an injection of an anti-hepatitis A antibody, where they artificially give you a shot of those antibodies because they know you're fixing to get hepatitis A. You understand what I'm saying? It's a way to like a short-term fix if you've been exposed. This is an example of artificial passive immunity, where you are given an injection of an antibody. That's what they're meaning. If you want to cross, I mean, a gamma globulin is an antibody. That's what that is.
That'd be like a tetanus shot too.
Yeah, exactly. After you step on a rusty nail, they'll give you a tetanus shot. What is that, 10 years? Oh, and you guys will have to have one of those too, but I think that's part of one of those other vaccinations.
That's part of the Tito.
Yeah. Okay, naturally active immunity is like, for example, you get that if you recover from a disease. If you've had chicken pox, right, because you recovered from chicken pox, you are gonna have an immunity from that, but it's because it is something that your body did naturally because you were exposed to that varicella zoster virus. And then artificial active immunity, that's gonna be, for example, if you're given a vaccination. Now that, you haven't had it yet, but you're gonna prevent it from happening by getting the vaccination.
The flu one? Yeah.
The flu?
Yeah.
Basically, naturally active and artificially active, if you think about it, you develop those antibodies because you worked for it, okay? You had the chickenpox virus, and you worked to develop that antibody. Or you were given a vaccination, you worked for that. Because you were injected with that inactive form of a virus, your body worked to produce that antibody. That makes sense? Okay, primary response and a secondary or anamnestic response to any type of infection. The primary response is when you are for the very first time exposed to something. This response will usually be slow and a small magnitude. The first thing that's gonna happen is you're gonna develop IgM antibodies. Those are the primary antibodies. Now, this is just generally speaking, some disease will vary from this, but you'll usually develop these, what's called IgM complete antibodies within 1 to 2 weeks. They're gonna gradually decline to undetectable levels within a few weeks or a month. At the peak, when you have the maximum, what's called IgM antibodies, you're gonna start to detect an IgG antibody. This is gonna increase for about a month. It says IgG levels will remain high for several months and then they will decline slowly, maintaining low but possibly detectable levels for years. The secondary anamnestic response occurs following re-exposure to the same antigen. We will instantly have large amounts of IgG that are produced. They will stay increased for a prolonged period of time and they will decline gradually. The best example I can give you of this is even though you get the hepatitis B vaccinations, like I'd gotten them and I worked at CHI I was probably there 6 years, and they said, okay, we're gonna test every employee at this hospital for everyone's hepatitis B antibody titer, okay? Some people, even though they're given the hepatitis B vaccination, if their titer is not high enough, they have to get the vaccination again, all right? And that happens occasionally. What they do to determine that is there is a test that they do called the hepatitis B, the anti-hepatitis B surface antigen. It is an IgG antibody that you can detect in people that have, basically their body has reacted to the immunization that they were given for hepatitis B. When they were given that vaccination, right, your body has to react in a way to where they're exposed to it. They instantly are going to develop an IgM antibody, but over a long period of time, eventually they're going to develop IgG antibodies. That means you have an immunity to the hepatitis B virus if you're ever exposed to it, okay? But again, that's where if you are exposed to it a second time after you've been given the vaccination, this is where that virus doesn't have a chance then, because your body instantly recognizes it for a second time. It has developed those memory cells that see that virus, instantly develops all those IgG antibodies. It tells you that. The main difference between primary and secondary responses is going to be due to the memory cells that have developed. Okay, the last thing, this is just basically a review of what we talked about. Again, just differentiating innate immunity and adaptive immunity. The type of response in innate immunity is antigen independent. It doesn't matter. As long as it is foreign, your body is going to react the same way every time. Okay, that's on innate immunity. That's what we're talking about, the macrophages and the polymorphonuclear cells, the phagocytosis, all of that. It does not matter what type of antigen it is, as long as the body sees it as foreign. Adaptive immunity is antigen dependent. We're talking about the second type of immunity, the one that's more complex, where your lymphocytes have to recognize it. In other words, a macrophage has grabbed onto that antigen and presented it, right, to those lymphocytes, and then the body has to determine what it's going to do with it. Okay, how it's going to recognize it, that has to do with adaptive immunity. Innate immunity is automatic, immediately, all right? When you're exposed to it, you have innate immunity. For example, remember the bee sting that we talked about. You're stung by a bee, instantly, redness, inflammation kicks in. That's when those macrophages and polymorphonuclear cells will respond. But in adaptive, you literally have a little bit of a lag time between exposure and the maximum response that the body will do. It determines, is it the first time it's seen it, or is it the second time it's seen it? That's what it's meaning by it doesn't necessarily occur automatically. How specific is the response? Innate immunity, it is not antigen specific. Adaptive, it is antigen specific. It has to recognize a particular antigen. There is really no memory involved in innate immunity, but there is memory involved in adaptive immunity. So anyway, this is something that you kind of put all the pieces together. All right, tomorrow, there's no perfect way to